All right, our next very clever idea. They're coming rapid fire, aren't they? You know, binary search trees, hash tables, heaps. Whew. Well, don't worry, we got plenty more to go. So, heaps. Well, let's introduce the heap. So while a BST would work for the purposes of implementing a priority queue, they're bad in some ways because you have to keep them bushy, which is annoying, and also handling duplicates is awkward. So what we're going to do instead is we're going to introduce a new type of tree that's going to have two properties. Okay? So the binary min heap is going to be a binary tree that is complete and also obeys the so-called min heap property. Okay? What's the min heap property? Well, the min heap property says every node is less than or equal to both of its children. That's different than the BST property. The BST property said everything to the left is smaller and everything to the right is larger. Now we're saying every node is less than or equal to both of its children, and we're going to allow duplicates this time. We're also going to insist on completeness. And this is a bit awkward, this term, but I think it'll become clear by example. But basically it's that if there are any missing items, if the tree isn't exactly filled out like this one is, then the missing items will only be at the bottom level, and all nodes will be as far left as possible. And we'll see some examples. So I could introduce a more mathematical definition, but it just didn't quite feel right in 61B. So here's a couple of different heaps. Here's a heap, right? This tree, every item is smaller or equal to both of its children, and there's no missing items, or if there are any missing items, it's only at the bottom level. This is also a min heap. Check out each item. Everything is smaller or equal to both of its children, and there are no missing items. Okay, here's another. Okay, well this one has a missing item in some sense, and by missing I just mean, well, it's not all the way full. The bottom level is not all the way full, and the only thing missing is over here, so all nodes are as left as possible. Here's one that is incomplete. So this tree, what has some items, there's only items missing at the bottom level, that's good, but they're not as far left as possible. And then finally we have this one here, which is lacking the min heap property. So what's wrong? Look carefully. 5, 4, right? So this should not be, 5 can't be 4's boss. That violates the min heap property. So let's see if those make sense. What I'd like you to do is consider these 4 trees down here and ask how many of them are binary min heaps. Okay. So you should pause. Okay, so I will go through them. This one right here, right? It's only missing items at the end, and everything is less than or equal to its children, so that one's good. This one, well, it's missing items not just at the bottom level, right? This tree is not complete in the sense that, you know, it almost fills itself out. There's a missing item at the second level, and some items at this third level. Or maybe we'd call this the first level, and this the second level convention. How about this one? Okay, we look at it. This is not less than its left child. This is actually a binary search tree. This is not a heap. And then finally this one. Okay, well, every item's less than both of its children. Is it missing items? Yeah, in a way. Are they only at the bottom level? Yes. Is everything as far left as it can go? Yes. So this is good, this is good, this is bad, this is bad. Alright, so those are heaps. You should be asking yourself, what good are heaps though? Okay, I get it, there's some kind of tree. Always a good question to ask, like, why are we learning this thing? Well, turns out that they're a very good way to implement a priority queue, as we've been alluding throughout lecture. So here's a hopefully easy question. Suppose you have a heap, right? Here's the heap, which contains values 0, 5, 1, 8, 8, 6. They've all been added somehow to this heap. If this is supposed to be a priority queue, how would you support the get smallest operation? This question, possibly so easy it's confusing, but think about it. Okay, so you just return the root. If this is a heap, then get smallest, you just return the root. Okay, if it's supposed to be a priority queue. So now I'm going to have a really hard challenge for you. Okay, so this is a blue slide, interview style question. I would like you, given this idea of a heap, everything we've learned so far, come up with an algorithm for adding an item. For example, how would we insert 3? And I'm going to require your runtime has to be logarithmic. And if you want, you can also try and come up with an algorithm for remove smallest. Okay? So maybe sit down and there's many possible approaches, but there's one best approach. And this is actually a very clever, the correct answer is super clever and cool. So I'd like you to try and see how close you can get. Okay? So maybe give yourself 5, 10, 15, maybe 20 minutes to actually really hammer at this thing and figure out how can I add to a tree in a way that feels symmetrical and elegant and beautiful and fast. Okay? So give it a shot. I'll be waiting. Alright, I'll spoil it by giving you guys a little animated demo of the usual solution. So what we could do, if we want to insert 3, okay? one approach you might have, and actually you might consider pausing if you got a little stuck there and working from wherever I am. But what I want to do is note that when I insert 3, I want to make sure I can maintain completeness, right? Completeness is fundamental. So the most natural thing to do is to add the 3 to this position because I maintain completeness. However, there's a problem here, right? So even though this tree is complete, it does not obey the min heap property, right? In particular, 5 is bigger than 3. So actually, one solution, and the solution that is typically done, the best solution, is to say, okay, well, 3 ought to be bigger than 5, so I'm going to swim up. I'm going to say 3 and 5 swap. Okay, so now 3 is here. So this is better. This thing right here, this is a heap. If you look at this little tiny world here, a heap is a recursive data structure, just like a binary search tree or a list. So a heap right here, this is a little heap, but the problem is that this heap is not a heap with respect to the larger context. So 3 is still, in this case, out of order. 5 and 3 are reversed, so 3 will swim up the hierarchy to its rightful place, and it declares, finally, this is my true place. Okay, so that's insertion. Let's see another example. Okay, let's say we want to insert 5. Well, again, because we want to respect completeness, we stick it in this location, in the place it needs to go, and then we're going to swim our way up the hierarchy. Okay, so we notice again, 5 and 6 are out of sorts. So what'll happen now, 5 will climb, and now 5 is above 6, which is good. And how about 1, right? Should 5 get above 1? No, right? 5 is bigger than 1, so it ought to stay below. So he says, I am home. For the first time in my life, I am home. Good, 5. Glad you're there. Okay, so that's insert. So if you didn't get delete yet, maybe ponder taking that as inspiration and try and come up with a delete algorithm. So how do I delete the minimum? Well, the minimum we know is always going to be in the root, so we need to somehow get rid of it. And so a common approach is, again, to respect completeness and to take this item and we'll move it into the root. So what I mean by that is, okay, we're going to swap the last item in the heap, this one right here, into the root. So we'll note both these guys, okay, right? So 1's getting removed, 6 is getting promoted, far above its station, and ends up being put up here. Okay. So now what we need to do is take into account the fact that 6 is not cut out to be the boss of this whole heap, right? We just grabbed it from the bottom of the hierarchy someplace, and while he might be somewhat qualified, he's certainly not going to be equipped to be running this entire giant heap. So what we're going to do now is basically a Darwinian battle, where we're going to say which of your 2 subordinates is more suited to rule the heap. And so what we'll do is, since 1 is smaller than 3, and that's how we're determining as the boss, 1 will tell 6 to move aside, and 6 finds itself here. Again, 6, not actually quite qualified to rule even this little heap. So he's going to trade with whoever is below him, and 3 takes over. Okay? And now 6 is finally in its place. Okay? Let's try again. So if you haven't, even if you didn't come up with that, try and figure out what happens when we delete 1 next. Okay, so I'll wait. Okay, so again, we need to swap at the last item in the heap, and in this case, it's not going to be 6 again. It's actually going to be 5. It's the last item in the heap scanning all the way over. So this is the one we need to move to the top. And so now 5 finds herself in charge, so going to get sent up to the top, and is now in the root. Now in this case, 5, again, she is not equipped to run this whole heap. She was taken from the bottom level of the hierarchy, so she's going to descend the heap. Now it turns out in this case, we could actually take either choice, because both 3 and 3 are equally qualified to run the heap. So 5, maybe she arbitrarily decides to head here. Okay. So now here's 5, but now 5, well, being quite skilled, she's going to say, I'm not going to descend further, right? She is actually qualified to run this little sub-organization, even though she wasn't able to do this top one. So she says, I won't descend further. Okay, so that's heap deletion. So I hope you actually gave it a shot and found that process of trying to add and remove from a heap to be useful. But yeah, it's a really great, very clever, and just beautifully simple algorithm. So to summarize this simple, powerful, and beautiful data structure, if we want to use the heap to implement a priority queue, well, we have 3 operations we need to be able to handle, not counting size, which should be fairly trivial. So we need get smallest. And in that case, we just return the item in the root node. Nothing else to it. How about add? Well, basically, we take this new employee X, we stick her in the last position, and then promote her as high as she can go until she can't get any higher. And then finally, we have remove smallest. So what do we do with remove smallest? Well, in that case, we're going to assassinate the president of the company, promote the rightmost person in the company to president, who may be wildly unqualified to be president, and then demote him repeatedly, always taking the better successor. And again, here's our animated demo we just saw. So a remaining question then is, how would we do all this in Java, right? We have the ideas here, but now we want to try and translate them into code in some way. And that'll be the subject of our next segment.